Morning, everyone. How are we doing? Come on in. Morning. Questions while we wait? Anybody? No? We're good? Let's wait another minute or two. Yep. Yeah, we're going to do the whole week on graphing. We have plenty of time. Plus, it incorporates everything we've learned, so that's kind of nice. Yeah, I'm expecting the midterm marks at the latest over the weekend. Okay, it's almost finished. No idea about the average yet. I haven't even looked at the marks. All right. Limit as x goes to infinity of this. What I would do, well, first of all, as x goes to infinity, I'm sure you've all realized immediately that this has the form infinity over infinity. I would not apply L'Hopital's rule immediately. What I would have done, because, I mean, why would I not apply L'Hopital's rule immediately? You're going to get, I mean, you know, first of all, the derivative of the denominator is going to be a product, so product rule applies to that. And it's going to make it more difficult. And as you go along, I mean, it's always going to have the form infinity over infinity, because you're not going to be able to cancel anything. So that's the issue. And the denominator will never disappear. No, not applying ln. No, I would just bring this back up. And rewrite it as e to the x to the 5 times e to the minus x over 5x, which is really e to the x to the 5 minus x. And now if you want to take a moment to convince yourselves that the limit as x goes to infinity of x to the 5 minus x, which has the form infinity over infinity, but you know what you're going to do, right? Maybe you're going to factor out an x or an x to the 5, whatever you want to do. You'll get the same answer as x goes to infinity, this goes to infinity, this goes to infinity, so the whole thing is infinity. So this has the form infinity over infinity. And now if you apply L'Hopital's rule, one time you're done because the denominator disappears. by disappears, I mean what do you want to mean? Derivative of the top, exponential times the derivative of the inside, 5x to the 4 minus 1 over 5. No, Jacob. You know the no. No, because you're not dividing the exponents. You're subtracting them. And what did I mean by disappears? I mean that it's no longer infinity here. So you're done. No more L'Hopital's rule. This, we just saw, went to infinity. So this is e to the infinity, which is infinity. This goes to infinity, and infinity minus 1 is infinity. Infinity divided by 5 is infinity. We're done. I didn't really. Jennifer's asking, how did I know not to use L'Hopital's rule right away? I didn't, but you know, if you use L'Hopital's rule right away, you see what's happening. Right at the top, 5x to the 4, e to the x to the 5. And the bottom, if you leave the 5 outside, you get e to the x plus x e to the x. And the point is that it's getting worse. You're applying L'Hopital's rule in the hopes of making everything simpler, and it's really getting worse. And if you keep going, right? I mean, because you still have an infinity over infinity, and now it's a product rule in the numerator, which is going to be a lot of work. And you still have a product rule here, and then you still have the, I mean, it's not getting simpler. It's not getting simpler, it's getting worse. Well, e to the x to the 5, as you've written into the first thing, is questionable, right? E to the x to the 5. It's not really clear what that means, right? So we probably should have brackets, right? That's slightly ambiguous. If you applied ln first, might work. It might work. So Jacob was, Matthew was suggesting to apply ln, to take ln of the whole thing. It's not a bad idea. Not a bad idea. Try it again. See what happens. Well, if you got e to the infinity, then it's infinity and we're done. Michael is asking if there's a simpler way to take the second derivative of this big expression. Notice you could combine it as x plus 2 times the square root. I suspect that's the best way to go. All right, let's get back to graphing. I can expect it to be messy and difficult. What I'm going to suggest is try to simplify as much as you can. If it's a question that is asking you for intervals of concavity, then it should be relatively doable, right? The questions in the book are not impossible, so it could be slightly difficult, but it has to be doable. Consider this. Consider this. We're going to graph that. What is the domain? Domain, you know what it is. All real numbers except plus or minus 5. Negative 5 as well, right? Because negative 5 will make the denominator 0. But perhaps you're thinking to yourself, well, I can simplify that by factoring out an x. And then these just cancel out. Indeed, they do cancel out as long as x is not negative 5. So if your domain is everything except plus or minus 5, in other words, if your domain does not include negative 5, then you can cancel them out. So your function, this complicated thing, is actually this simpler expression as long as x is not negative 5. So we're going to have some sort of hole at x equals negative 5, exactly that. X and y intercepts. If x is 0, y is equal to 0. And if y is equal to 0, then it's easy to see that x has to be 0 as well. So there's only one x and y intercept, and that's the origin. Very well. Let's take the derivative. Quotient, so quotient rule applies. VU prime minus UV prime all over V squared, which is really just 5 over 5 minus x all squared. We'll see if we can fit something in like that, Matthew. I don't know that I have anything today. Maybe I'll try to come up with something for next time. Critical points. Critical points, anyone? 5, except that I'm sure Sean will do a final review. Absolutely. Right, so normally 5 would have been a critical point, but 5 is not in the domain. So there are no critical points here. Let's do a first derivative chart. Labeling critical points and points that are not in the domain. There are no critical points, but plus or minus 5 are not in the domain, so we need to throw those in. If you take, well, I mean, if you look at your derivative, numerator is always positive, denominator is always positive. So the derivative is always positive regardless. Your function is always increasing. All right, let's move on to the second derivative, which is easily seen to be 10 over 5 minus x cubed. Possible points of inflection. Possible points of inflection. None, thank you. Because again, 5 would have been a possible point of inflection, but it's not in the domain. So there are no possible points of inflection. Let's draw a second derivative chart nonetheless. Labeling possible points of inflection, there are none, and points that are not in the domain. Is there not a negative for the 10, right? Because this is 5 times 5 minus x squared, x to the negative 2. So when you differentiate, you get a negative 10, blah, 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 to the negative 3, but then you differentiate the inside. Chain rule, right? And the derivative of the inside is negative 1. So, negative, negative. A linear function doesn't have concavity, that's right. The second derivative is 0. Right, so it could be viewed as both concave up and concave down, right? It's like, it's the limiting case of concave up, concave down. If you take a number less than negative 5 and plug it in, first of all, numerator is always positive. So if you plug in negative 6, you get 11. So the whole thing is positive. Your function is concave up. If you plug in 0, 10 over 5 cubed, positive. And if you plug in 6, 5 minus 6 is minus 1 cubed is minus 1. The whole thing is negative. What is happening at 5? Five is, it was a trap. It was a trap. It was a trap, people. 5 is not in the domain. 5 is not a point of inflection. Right? We even say here, no possible points of inflection. We're almost ready to graph. I prefer concave up, concave down. I think it's more indicative of what's happening. Yeah, so I prefer that, and so do most books. So we're almost ready to graph. We need to, isn't it technically positive after 5? If you take a number bigger than 5, 5 minus a number bigger than 5 is going to be negative. And when you cube a negative number, it still remains negative. So numerator is positive, denominator is negative, the whole thing is negative. We need to know where to start, where to end. Right, we're graphing from left to right, so we need to understand a limit as x goes to negative infinity of your function. And what is happening here? This has the form infinity over infinity. So we can do L'Hopital's rule. A quick L'Hopital's rule gives us a 1 over negative 1, which is negative 1. Limit as x goes to positive infinity of x over 5 minus x. Same thing, right? This still has a form infinity over infinity. And the limit, so I mean a quick L'Hopital's rule, also gives you 1 over negative 1, which is negative 1. Benjamin, when if x is equal to 0 and y is equal to 0, we're just looking at the x and y intercepts. You know, I mean, if you think back to high school, these were important points where the graph crosses the x-axis or the y-axis. Right, so if x is 0, you get 0 over 5. You get 0. And if y is 0, if this whole thing is 0, what values of x make that 0? Well, there's only one, x equal to 0. Shamir, I don't know what you mean by using logic. So let's try to stay away from not showing any work. You want to show the work. Show the work here. It's L'Hopital's rule. It's one step. No, don't use that. Don't use x squared and negative x squared being the only important terms. Show all your work. It's one L'Hopital's rule step. You want to show all your work. Will we be expected to find the value of the whole? Indeed, we're going to do that right now. E to the infinity is not an indeterminate form. Correct. Because e to the infinity is infinity. There's no ambiguity there. You know exactly what it is. Right, so we found limits as x goes to negative infinity and x goes to positive infinity. We know where to start, where to end. But now if you look at your domain, plus or minus 5 are not in the domain. The obvious question arises, what's going on there? How does your function behave at or near 5 and negative 5? These are important questions that will be reflected in our graph. So let's investigate. What is happening as x goes to negative 5 from the left? Correct, Matthew? E to the infinity is infinity. You know the graph of e to the x. As x gets larger and larger, so does the exponential function. We have this limit. Limit as x goes to negative 5 from the left. You know what to do when you're looking at limits. First thing to do is plug in. What happens if we plug in? We get negative 5 over 10. Negative 5 over 10 is negative 1/2. There's no ambiguity here. There's no 0 over 0. Plug in and you get an answer. It's a rational function. If you get an answer, you're done. Limit as x goes to negative 5 from the right. Same thing. Negative 1/2. What about near 5? Limit of spot as x goes to 5 from the left. If you plug in, what are we looking at? If you plug in, you have a 5/0. You know, in the context of limits, this is some sort of infinity. 5/0 is some sort of infinity. All we have to do is determine if it's positive or negative. Numerator is close to 5, so that's going to be positive. If you take a number less than 5, 5 minus a number less than 5 is going to be positive there as well. So positive on top, positive on the bottom, positive infinity. Similarly, limit as x goes to 5 from the right. If you plug in, you get a 5/0. So again, some sort of infinity. I mean, you want to be careful, right? I mean, a lot of people are going to jump to saying, well, they have to have different signs. They don't. You should take a moment to work it out. If you plug in 5, so if you take a number close to 5, the numerator is going to be close to 5, so positive. 5 minus a number bigger than 5. 5 minus something bigger than 5 is going to be negative. So positive on top, negative on the bottom, the whole thing is negative. Matt is asking, since you know it's always increasing, do we have to show our work for the limits at 5? Absolutely you do. You do have to show your work, and this is going to be beneficial for you. This is going to tell you if a mistake has possibly been made. It's going to help us to check if our work makes sense. Benjamin is asking, what is a negative infinity? First of all, it's some sort of infinity because it has the form 5/0. So some sort of infinity. And when x is close to 5, the numerator is close to 5. So numerator is going to be positive. And 5 minus a number bigger than 5. 5 minus the number bigger than 5 is going to be negative. So positive on top, negative on the bottom. The whole thing is negative. Let's graph. So what are we saying? What are we showing here? We're noticing that at 5 you have a vertical asymptote. Five and minus 5 are not in the domain. But at 5, something more happens. So let's get ready to graph. Where are we starting? Leftmost. So at negative infinity. And when you have very large negative numbers, the function is very close to -1. Question, are we above -1 or are we below -1? If you plug in a large negative number into this, like -1,000,000, well, let's say -100,000. This is -100,000 over 100,005. So this number is a number very close to 1, but just less than 1. Well, strictly less. So if you multiply the whole thing by -1, then you know the inequality reverses. So it's going to be a number just slightly larger than -1. So as Shamir suggests, it's above. And Kamal is saying it's above since the y-intercept is at the origin, but here's the misconception that a lot of students have. A lot of students believe that you cannot cross the horizontal asymptote. It's not true at all. Not true at all. Your function can cross the horizontal asymptote. There's no issue there. So let's not use that fact to say that it starts above, but rather let's test to see what happens. So you are above the horizontal asymptote. What is happening? You are increasing concave up all the way to -5. What is happening at -5? As you approach -5, you're getting closer and closer to 1/2. So increasing concave up all the way to -1/2. Jennifer's correct. There would have been a local minimum, but what if you made a mistake, right? What if something happened? So this is really a way for you to make sure that your work is correct. So don't assume your work, but rather test it some other way so that you're able to make sure no mistake has been made. And as Matthew suggests, horizontal asymptote should only be followed in the end behavior, right? It's a behavior for large values. But even then, it could still cross a horizontal asymptote. I'll give you an example of that in a moment. So increasing concave up all the way to -5. After -5, you're still increasing, still concave up all the way to 5. What is happening at 5? As you get closer and closer to 5 for numbers less than 5, the function is going to positive infinity. So increasing concave up, going through the origin, right? We knew that. And there it is. After 5, where are you? After 5, you're at negative infinity. You better be increasing, right? So again, this is a way for you to verify that your work is not incorrect. You are increasing. Concave down now, forever. And where's the forever taking us? Closer and closer to -1. Increasing, concave down, getting closer and closer to -1. There we have it. Very nice. Let me give you an example. And he's asking, how do we determine if the function is above or below the horizontal asymptote? Check it. This is our function. Take a large negative number. If you take a large negative number and you plug it in, like -100,000, you had -100,000 on top and 105,000 on the bottom. That is bigger than -1. So it starts right above. Matthew's asking, do we do the same check on the right to see if it crosses? On the right, if it crosses, then it would have to come back down. And we don't have that in our first derivative chart. You could check that for large values of x, your number, what would that be? If you plug in 100,000, that would be 999,995 with a negative. So you could check that this is actually just a bit less than -1. Yeah, we'll do some more graphing. One more example today, and more examples on Friday. Absolutely. Right, because I mean we're running out of material, and graphing is nice because it incorporates everything we've done so far. So we can take our time here and do several examples. I was going to give you an example of a function which crosses the horizontal asymptote. Let me do that now. Consider this function. Right, this function has a horizontal asymptote of 1, and it crosses it infinitely many times. There it is. What do we say the function is not differentiable? Well, the indifferentiable, I don't know that we use that word, but not differentiable, let's say. Not in this case though, right? I mean, it was nice and smooth. The function would be differentiable. Matthew was asking, how is that a horizontal asymptote? Well, what does a horizontal asymptote mean? It's the behavior of your function as x gets very large. And you see that the function was getting closer and closer to 1. When is your next physics quiz, Matt? We will do oblique asymptotes on Friday. Absolutely. But in the meantime, let's consider this. When is the physics quiz? Because we can do antiderivatives before we do anything else. Well, let's do this example, and then I'll tell you what an antiderivative is. It's nothing. It's nothing. You already know everything you need to know. What else do we have left? So we'll do oblique asymptotes on Friday. Optimization, so word problems. Again, you have all the information you need. Antiderivatives, but you have all the information you need. And maybe we'll discuss Newton's method. Yeah, exactly. You don't need antiderivatives, but I'll tell you what they are anyways. It's just notation. But let's graph this first. What is the domain? You know what it is. What values of x can you plug in? All real numbers. X and y intercepts. You say except for one, but one's not an issue, right? You can plug one in and you get a number. If x is 0, y is easily seen to be 1. And if y is 0, in fact, as Matthew points out, when y is 0, x is 1. Right? So x equals 1 is actually the x-intercept. Excellent. Let's move on to the first derivative. This is a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leaving the first one fixed, differentiate the second one. Which is easily seen to be negative x e to the x. Is it easily seen to be that? Critical points. X equals, you know what it is. X equals 0. Let's draw a first derivative chart and see what happens. If you plug in a negative number, the exponential is always positive. Negative here, negative there, makes everything positive. And if you plug in a positive number, this is positive, that's going to be negative. So decreasing here. You see what's happening at 0? What is happening at 0? We have an absolute maximum at 0. Absolutely. Let's move on to the second derivative. Product rule again, right? Can we cross vertical asymptotes? That you cannot. Well, I mean, again, your function could be defined at that point, but by definition of a vertical asymptote, you need at least one of the sides to go to sort of infinity. So you're not going to cross it in that respect. Yeah. How do we know it's absolute and not local? Right? Your function is going to increase. First of all, the domain is all real numbers. That's very important. And then your function increases all the way to whatever it is at 0, and then decreases afterwards. So it never comes back up to cross it again to a higher level. Why can we not cross them? Let's postpone that discussion until we finish graphing, and then I'll show you what I mean by crossing versus not crossing. Everybody comfortable with this as the second derivative? Let's factor out a negative e to the x. Thank you, Matt. And we see possible points of inflection as -1. Answer for the first derivative, it's a product, right? So product rule applies. Differentiate the first one, -1, leaving the second one fixed, plus leave the first one fixed, differentiate e to the x, whose derivative is e to the x. Expand all of that. This cancels with this 1, leaving you with a negative x e to the x. Exactly that. And the first two terms cancel. Precisely. Second derivative chart, labeling our possible point of inflection. If you take a negative number, maybe -2, -2 plus 1 is negative. The exponential is always positive, so negative, positive, negative, the whole thing is positive, meaning your function is concave up. If you plug in 0, this is 1, this is 1, with a negative there, the whole thing is negative, so you see that in -1 you have a point of inflection. We need to know where to start, where to end. What is the limit as x goes to -infinity of 1 minus x e to the x? As x goes to -infinity, this goes to infinity. E to the -infinity is 0. So this has the form infinity times 0. What are you going to do? You know what you're going to do. What are you going to do? Manipulate in the hopes of using L'Hopital's rule. But not right away, right? You have to bring it into the form 0 over 0 or infinity over infinity. And let's do so by rewriting it this way. 1 minus x over e to the minus x. Yeah, exactly, Michael. Thank you. The usual trick, or with a negative exponent instead. And now as x goes to -infinity, this goes to infinity, e to the negative infinity, so e to the infinity, which is infinity, this now has the form infinity over infinity. Everybody comfortable with that? Whose limit is? Well, I mean, we want to do a L'Hopital's rule. Derivative of the top, derivative of the bottom. And as x goes to -infinity, this goes to infinity, e to the infinity is infinity. So 1 over infinity is, you tell me, you know what it is. Similarly, limit as x goes to positive infinity. Thank you, everyone. Limit as x goes to positive infinity. This goes to infinity. 1 minus infinity is -infinity. This goes to infinity. -infinity times positive infinity is -infinity. Don't assume that the same behavior is going to happen on one side and on the other. There's absolutely no reason to believe that, right? Whatever happens for large negative numbers has absolutely no bearing on what happens for large positive numbers. And these two limits are treated in different ways. So don't assume the same thing happens. Don't assume that you treat the limits the same way. There's absolutely no reason for that. All right. So we're going to graph from left to right. For large values of negative x, or for large negative values of x, the function is close to 0. Are we above 0 or below 0? If you plug in a large negative number, first of all, this is going to be positive. If you plug in a large negative number, 1 minus a large negative is going to be positive. So positive, positive, you're just above 0. What's happening? Increasing, concave up, all the way to -1. Increasing, concave up, all the way to -1. After -1, what's happening? You're still increasing, but now concave down all the way to 0. Increasing, concave down all the way to 0. At 0, we were at 1. Afterwards, what is happening? After 0, you're decreasing, concave down forever. And where's the forever taking us? To -infinity. Decreasing, concave down, all the way to -infinity. We cross the x-axis when x is 1. We have an absolute maximum here of 1. And we had a point of inflection right here. It would be nice to calculate the y value when x is -1. This is 2 over e. So it's nice to point that out as well. Do we not need to know the y value of the point of inflection? It's nice to calculate it. You should do that. And is asking us to go over the limit as x goes to infinity. Just plug it in. Right? That's the first thing you want to do when you have a limit. Plug it in. To see if you get an answer. And in this case, we do. If x is infinity, 1 minus infinity is -infinity, right? 1 minus a very large number, it's going to be a very large negative number. This, e to the infinity, is infinity. So this is infinity times -infinity. A large negative number times a large positive will give you a large negative. Yeah, it's all good. And there it is. Very nice graph. Right? Not a function that you should know the graph of before graphing it, so that's nice. And I mean, all the work you do leads you to this graph. How are we doing here? We were going to discuss something else, which has now escaped me. What did we want to discuss? We were going to talk about something. I forget now. Let me scroll back up here. Yes, vertical asymptotes. That's right. Well, vertical asymptotes first, and then quickly antiderivatives. Quick questions here before I rub this off? No, we're good. Well, there was talk of crossing vertical asymptotes versus not. And here's what I mean. If you have a vertical asymptote, that means that at least on one side, your function has to blow up to positive infinity or negative infinity. So you could have something like this, where it blows up on one side, but have this there as well. So while you're not crossing it, your function is still defined at the vertical asymptote. So, you know, I mean, that's a possibility here. That's all I wanted to say about that. Right, so here, x equals a would still qualify as a vertical asymptote. And for those of you doing physics, but really for everybody, because that's going to be our last topic, antiderivatives. Can you have a case like in the horizontal asymptote where it crosses to the other side? Well, that's the thing, right? I mean, you're not going to have something like this or something like this, because by definition of a vertical asymptote, it has to go to infinity or negative infinity on at least one of the sides. And of course, you're not going to have something like this, because that's no longer a function by the vertical line test. So none of that. Antiderivatives or integrals, it's the opposite of what we're doing. We're doing derivatives. Antiderivatives is the opposite. So if you have a function x squared, you know the derivative. You know the derivative of x squared is 2x. In antiderivatives, so instead of going forwards and finding the derivative, you kind of want to go backwards and find a function. Find a function big F whose derivative is x squared, is the function you started out with. So it's the opposite of integration. It's the opposite of differentiation. It's the antiderivative or the integral or integration. Exactly, Morgan, right? So we're looking for a function whose derivative is x squared. Well, you're very familiar with derivatives. You're now masters of differentiation. So in this simple case, you can come up with an antiderivative. What function has derivative x squared? Work backwards. Anybody? X cubed. But you know the derivative of x cubed is 3x squared. We don't want the 3. Can we get rid of it? 1/3. There it is. Right? The derivative of 1/3 x cubed, you leave the 1/3 out, differentiate the x cubed, bring the 3 down to cancel with this, leaving you with the required x squared. But now let's think back to the mean value theorem. One of the implications of the mean value theorem was that if two functions have the same derivative, then they had to differ by a constant to begin with. And you know the derivative of a constant is 0. So 1/3 x cubed has derivative x squared, but so does 1/3 x cubed plus 4. And so does 1/3 x cubed plus 14, and so on and so on. In general, if you add any arbitrary constant, this is the general antiderivative. We have notation for the antiderivative. If you start with a function x squared, the antiderivative, or the integral, or the indefinite integral, these are all words that mean the same thing. The antiderivative of x squared is 1/3 x cubed plus c. So this is going to be notation for the antiderivative. And because you know the derivative, then you know the antiderivative for a lot of easy cases. What function has derivative x to the 5? What is the antiderivative of x to the 5? You tell me. Can you come up with a function whose derivative is x to the 5? 1/6 x to the 6, right? In the same way, right? If you differentiate x to the 6, you get 6x to the 5. This 1/6 cancels that 6, and you're done. Exactly that. What about cosine x? Is that a line before the function? You mean this? It's the symbol. It's like an elongated S. An elongated S. As for some, we'll understand why that is in Cal 2. Right? So here we're asking the question, what function has derivative cos? You know that it's sine. Exactly that. What about secant squared? What function has derivative secant squared? What is the antiderivative of secant squared of x? As Maddie points out, tangent. The derivative of tangent is secant squared. And that's the beauty, right? When you write something down, you can check your answer here. If you differentiate this right-hand side, you have to get this thing back. Exactly that, Michael, right? S as in sum, because it's going to represent the area underneath the graph. Absolutely. But we'll see all of that in 141. Right now, for the next 2 or 3 minutes, let's just have fun looking at some antiderivatives. And what function has this as its derivative? Thank you. Arc sine. Arc sine, well, Sean, not so much. Not so much, and I'm going to invite you to take the derivative of what you wrote down. When you apply the chain rule, you see that an extra negative 2x is coming in, which is not what we're looking for. What function has this as its derivative? R10 indeed. Right, I mean, trivially. Now, in the same way that you know the derivative to be linear, right? The sum, the derivative of a sum is the sum of the derivatives. And the derivative of a constant times a function, you can just differentiate the function and multiply the constant back in. The same has to be true for the antiderivative, meaning that you could split this up into 3 different antiderivatives. Antiderivative of x squared, 1/3 x cubed. Antiderivative of x, 1/2 x squared. What function has derivative -6? -6x. Throw in your arbitrary constant at the end, and there it is. So that's the idea behind the antiderivative. If you are comfortable with the derivative, then you should be very comfortable with these easy antiderivatives. Of course, as you know, or as you may know, 141 is devoted entirely to finding antiderivatives. So of course, these get more and more complicated. But as far as we're concerned, if you can spot the antiderivative, that's all we're going to, at least for this course. And I suspect probably for physics as well. Michael, go ahead and ask your linear algebra question. Wait, aren't you guys having a linear algebra midterm right now? It's over? Okay, very well. Yeah, so lecture's over. Thank you all for coming. If Michael had a linear algebra question, we can answer that now. Maybe we can answer. We'll see. Very good. So go ahead and if you were to prove that a vector exists in 2 different planes that goes through the origin, sure. Can I just take the cross product of the normal vectors for the 2 planes? Fine. I mean, what? We are done with class, thank you. Fine. So all the vectors going through the origin would so really line. You get a line, right? So were you going to give the parametric equation of that line? Was that your goal there? And were you given the actual 2 planes, or it was just a theoretical question? Yeah, so I would have gone with the cross product. Exactly that. Yeah. The cross product is going to be a vector perpendicular to both normals. So it had to live on the first plane and it had to live on the second one as well. So it lives on both planes. And then just make sure that it goes through the origin. Yep. Sounds good. Very good. Thank you all for coming then. You guys have a good one. I will see you on Friday.